So in this section, we're going to talk about what happens when your data is very spread and what methods we could do to identify these spreads. So to begin, I kind of want to do this simple example. So let's say you have this data set of average monthly temperature for two different cities, San Francisco and St. Louis. So let's compute their means. And from the previous section, this should be pretty fast. So let's consider the population mean for San Francisco. So remember, we have to add up all of our data values and divide it by the number of observation in your data value. So the mean temperature for San Francisco is 57.5. Now we kind of do the same thing for St. Louis. You find the mean by adding all the values and divide it by 12. And so the average temperature for St. Louis is 56.1. We kind of noticed that the average temperature for both San Francisco and St. Louis are very close to each other. So this kind of begs the question. So let's ask a question. Since the mean for both cities are very close to each other, does this mean the temperature are similar for both cities? And of course, the answer is no. If you look back into our data, St. Louis has a much wider spread of temperature. So what does this mean? So that means that the mean or the average does not tell us anything about how spread out our data are. So we have to figure out something different. One thing we could do is take the range of our data. And the range is just taking the difference between the largest value and the smallest value of our data. So let's compute the range for the temperature for San Francisco and St. Louis. So the range for San Francisco will be 63 minus 51, and 63 is the biggest value in the data set, and 51 is the smallest for San Francisco. And that will give you 12. So the range for St. Louis will be 79 minus 30, and remember 79 is the biggest temperature in San Francisco, and 30 is the smallest, and it will give you 49. This is a really big difference. So this kind of tells you that the range is much larger for St. Louis, which kind of indicates that the spread in the temperature is much greater there. But in practice, usually the range doesn't really tell us much, and so people kind of stay away from it. So that's why we have to figure out a new method. So the range is easy to compute, but typically not used in practice. So we use something called a variance, and what variance does, it kind of tells you or measures you how far away your data value is from the mean, and that's important because if your data has a small amount of spread, then most of your values will probably be really close to the mean. But if your data set has like a larger amount of spread, then a lot of your data values is far away from the mean. And that's typically what variance is measuring, is how far away your data value is from the mean on average. So how do we compute this? So remember, just like there's two types of mean, there's actually two types of variance. And a little reminder that when we're dealing with samples in population, a sample, say this is a sample, it's just a subset of a population. right? And we could do some analysis on your population, and we could do some analysis on your sample. So let's talk about your population variance. Your population variance is denoted by something called sigma square. This symbol here is a Greek letter. It's just called sigma. So to compute this, you take the sum of your data values minus the population mean, you square it, and divide it by the total number of observation in the population. So here, we already know how to compute your population mean. So once we have that, for each data set, we're subtracting it and we're squaring it. And then we're adding all those value up. So the same thing with sample variance, we denote it with s square, and s is just s. And to compute this, we take a summation of all of our data values minus the sample mean, squaring it, and then adding all of everything else. The difference here is that we're dividing by n minus 1 rather than just n. So that's the big difference between the population variance and the sample variance. So it is kind of time consuming to compute variance, but it just kind of takes a lot of practice. So that's what we're going to do next. So let's compute the population variance for San Francisco temperature. And since we're dealing with a population variance, we're going to divide everything by n rather than n minus 1. So we have to compute the population mean, and since we already did that in the previous example, we know that it's 57.5. To make it a little easier, I made this little chart. On the left column, we write down all of our data values, or our x's. Notice that we don't need to put them in order. It doesn't really matter. Then on the second columns, we want to compute x minus mu, which is our population mean. So we take 51 minus 57.5, which gives us negative 6.5. So what we're doing is taking our value and subtracting it from our population mean, and we're just collecting them. So we're going to keep this pattern going all the way through. So once we have all of our values for x minus mu, we want to square them, because in our formula, we have to take a summation of all of these values square. So we take these values, negative 6.5, and just squaring them. Notice that all the negative values, once we square them, they become positive. So this tells you that your variance will always be positive. So you keep this pattern going all the way through. So once we have all of our values, we have to take a summation of all these x minus mu square, which means that we just have to take the sum of all these values. Remember that this fancy e is a summation. We're just taking the sum. So if we add all these, they'll actually become 169. But are we done? No, because remember in our formula, we need to take the summation of x minus mu square and divide it by n. And since we're dealing with a population variance, we're dividing by n and not n minus 1. So the final answer should be 14.083. Also, let's write a little note for ourselves saying that our variance is always positive, which means that if you did a calculation and you got a negative number, then you have to go back and figure out where you went wrong, because that's impossible. Our variance should always be a positive number. So let's look at this example. So a company that manufactures batteries is testing a new type of battery designed for a laptop computer. They measure the lifetime in hours of 6 batteries, and the results are these. So we want to find the sample variance of the lifetime. Since we are dealing with a sample variance, our formula is going to be a little bit different. The first thing you want to do is compute our sample mean. Since this is a sample mean, we're going to denote it as x bar. So this is just taking the sum of all of our data values and divided by 6. And this is 4. So I made this chart to make it a little bit easier. On the left columns, we're going to put all of our data values. And on the second column, we're going to compute our data values minus our sample mean. And we're going to keep doing this through all of our data values. So once we finish, we want to square all of our values because we're going to add them up later. And notice again that all of our negative values become positive. So that kind of gives you an idea that our variance will always be a positive number. Then you have to take the sum of all these values, which is just the summation of x minus x bar squared. So it's just adding all these up. And this should give you 10. But are we done? No, because remember that our sample variance, this is our sample variance, not our population variance, that's different, is equal to the summation of x minus x bar squared over n minus 1. We know the top one, which is 10, and the bottom is 6 minus 1, because the number of observation in our data set is 6. So we have a variance of 2. So variance can help you identify spreadness in your data, but it's kind of difficult to interpret this in the real world setting. So that's why we use standard deviation. And again, with standard deviation, there's 2 types: population standard deviation and sample standard deviation. And this is pretty straightforward because once you know variance, your standard deviation is just taking the square root of that value. And very similarly, you take the square root of your sample variance, and that will give you your standard deviation. Let's compute the standard deviation for the temperature for San Francisco. We know from the previous example, we calculated this as 14.083. So the standard deviation is just the square root of that value, which is just the square root of 14.083, which is 3.752. Then when we take the standard deviation of the battery life, we know that our variance is 2. So our standard deviation is just the square root of that value, which is 1.414. And notice again that I'm rounding everything to 3 decimal places, which is the norm. Once we figure out our standard deviation, now we're able to interpret what this means in real world words. And to do that, I came up with like a little guideline of what to say. So on average, and then you input the individual that you're studying, what it depends on the example, R, and then you input the standard deviation and their units away from the typical value. And you should probably fit this on the problem that you're working with. So for example, let's interpret the standard deviation of the San Francisco temperature. So following our guideline here, we could write on average, the average monthly temperature in San Francisco is about 4 degrees from the typical temperature. And notice that what I wrote down and my guideline is something very similar. Another way you can figure out how spread your data is something called the coefficient of variation. And what this is kind of tells you how large your standard deviation is relative to the mean. And this is really good when you want to compare data which has different units. So let's look at this example. So the annual precipitation in Atlanta, Georgia has a mean of 49.8 inches and a standard deviation of 7.6. And the annual temperature is 62.2 and with a standard deviation of 1.3. We want to compare each of these coefficient of variation. So the CV for precipitation is just the standard deviation over the mean. Since we already have these numbers, all we have to do is plug them in. So this is just 7.6 over 49.8, which gives us 0.153. And when we do the same thing for temperature. Since we already have the numbers, again, we just plug them in. And the CV for precipitation is a lot higher than the CV for temp. So that kind of tells you that the data in precipitation is a lot more spread. One last thing that I want to go over is something called the empirical rule. And this happens only when your histogram is approximately symmetric. Another word for symmetric is normal or bell shape. So what this means is that if your histogram is kind of symmetric, then 68% of your data is within one standard deviation from the mean. So what does that mean? Well, remember when we were talking about distribution of shape with mean, median, mode? We know that the mean, when it's symmetric, the mean is right in the middle. So this is your mu, because this is your average. So 68% of your data is one standard deviation away from your mean. So that means it's one, you add one standard deviation and subtract one standard deviation, and that's 68% of your data. 95% of your data is two standard deviation away. So kind of do the same thing where you add 2 times your standard deviation. So for example, if you had a mean of 5 and a standard deviation of 2, so then this will be 5, and this will be 5 plus 2, which gives you 7, and then this will be 5 minus 2, which gives you 3. So this is just telling you that 98% of your data is between 3 and 7 in this example. We're going to go through this a lot this semester, but for now, this is just a small introduction. Also, almost all or almost all of your data should be within 3 standard deviation.